Hi, folks. This is lesson 2 from Unit 4. So we're going to continue our work using this idea of radians as a measure for an angle. And now we're going to talk about something that's called angular speed or velocity. So think about in a car, one of the items on the gauge is the tachometer. It tells you how many revolutions per minute the wheels are turning at. Okay, now that again is something that's easy to identify. Everybody can imagine a wheel turning around and the number of times that it'll turn in a minute. Okay, but the way in which we study or calculate um, with this measure is not by calculating the number of turns per minute. That's sort of that's an easily understandable thing for the layperson. But when it comes to doing calculations, we actually look at the angle that it turns uh, per minute or per second. Okay, and in particular, we normally will use radians. Okay, so angular velocity is very often given in radians per second. So in other words, what's the angle that it turns in radians every second? Now, of course, if it's going very fast, it might turn more than one full turn. So it might be more than 2 pi radians per second. Okay, so what I want you to do here is figure out what 75 revolutions per minute. Okay, so wheel turning around 75 times in 1 minute, and try to determine that velocity as an angular velocity. Okay, in other words, you're just going to change the units from revolutions per minute to radians per second. Okay, so go ahead and do that. You should pause the video and we'll start up once you get back. Okay, so let's take a look at this question here. And essentially, this is just a change of units question, because what we have is we have that the wheel is turning at 75 revolutions per minute. Okay, now here I can do this in less steps, but I'm going to choose to do it in several steps here. So the first thing I'm going to do is I'm going to change revolution into angle. And we know that each revolution, each turn, is 2 pi radians. Okay, so one revolution, okay, is represented by an angle of 2 pi radians. Okay, so this is how I change um, revolutions into radians. I just multiply the number of revolutions by the angle in each one, which is 2 pi radians, and of course this is in 1 minute. Okay, but now we know that we don't want to know the number of radians in a minute. We want to know radians in seconds. Okay, so now I'm going to replace the denominator here, this 1 minute. This is number of radians in 1 minute, and just replace that by 60 seconds. Okay, so those of you taking physics and chemistry are used to doing this all the time. All right, so this now is 60 seconds. This is the number of radians. So now essentially we have it in radians per second. We're just going to simplify this as much as we can. Okay, so here we know the 2 and the 60. That'll reduce to 1 over 30. Okay, and now we've got the 75 and the 30. Well, definitely divisible by 5. So this is 15 over 6. And in fact, I can go even further because these are also both divisible by 3. So this will be 5 and this will be 2. Okay. So in the end, all of this, didn't even have to touch my calculator, reduces to 5 pi over 2 radians per second. Okay. So um, notice that if I want to give an exact answer, I do have to, work with this pi. And if I want to get an approximation, since this is an application type question, okay, here we can approximate 5 times pi divided by 2, and that's about 7.85 radians per second. Okay, now we have to remember that one turnaround is 2 pi. Okay, so that's about 6.28. So it means this is going around more than one turn in every second. Okay, so again, this is not something we're going to spend a lot of time working on, but it just goes to show that, a measure that we can imagine, speed of revolution, okay, or can be measured using this new unit that we've got to work with angle instead of working with something like the number of revolutions. All right, so now another thing we're going to look at is a relationship that we've essentially used already, but we're going to look at it a little more generally here. Okay, so let's just draw a circle. Okay, so here we've got a circle, and we remember that 1 radian was the angle produced by an arc, which represents just a segment of the edge of the circle, that if this arc was the same length as the radius, then that produces exactly 1 radian. Okay, and in order to determine the number of radians in a full turn of a circle, essentially what we said is well, okay, if each radius represents 1 radian, we ask ourselves how many radii can fit in the circumference of a circle. And of course, we figured out both by approximating and by using our circumference formula that it took 2 pi of these radii to form the whole edge of the circle. So that means it was 2 pi radians, about just over 6.28 radians to do one full turn. But what if we go just more generally? Okay, what if here I want to take some general arc, so not necessarily the full circumference of the circle. So let's call this A. Okay, so this arc is going to produce some angle. Let's call it theta. And is there a relationship like there was between the circumference, which would be the arc that goes all the way around the circle, this angle in radians, and the radius? Okay, so this is what I'm going to leave you to think about, is I'm trying to look for a relationship between these 3 measures in my circle. Okay, so go ahead, stop the video and see if you can figure out what that relationship is going to be. Okay, so we're back here, and I'm going to do essentially what we did before. Okay, when we worked with the circumference of the circle, I asked how many radii can fit into one turn around the circle. So what we did is we divided the circumference by the radius, and that tells me how many times the radius goes into the circumference. Well, I'm going to do the exact same thing except with this arc here. I'm going to ask myself, how many times does the radius go into this arc length? Okay, and I do that by dividing. So here there's 1 radian. Here's, another radian. And there's maybe, another radian. And then another little bit. So if I want to ask myself how many radii go into this arc length, I do that by dividing. But each of these radii is going to represent going around by 1 radian. So in other words, this is going to represent the number of radians in this angle that's produced by the arc length A. Okay, so exactly like we did for the full circumference, we divided the circumference by the radius, and that gave us the number of radians, because each radius along the edge corresponds to 1 radian of angle. We have this relationship here. And in fact, sometimes this is used to represent the uh, measurement in radians. Okay, essentially the angle in radians is represented by the arc length that produces this angle divided by the number of radii. Okay, and this formula you will often see written in this more familiar form. A equals r theta, which of course is equivalent. I just multiplied both sides of this relationship by r, or by that equation by r, and we get this alternative way of defining this relationship. Okay, so what we have here is we see how, an angle measured in radians, again, has a very physical relationship to the circle itself, or to any arc length. Okay, so you'll see some questions as below, and a couple of more interesting ones in the textbook for homework as to how you can use this relationship between the arc length, the radius of the circle, and the angle that's produced by that arc length. Okay, so now take a couple of minutes to answer questions 3, and also to think of questions 4. Okay, so I'd say that should take you about 5-6 minutes to solve these, and then we'll come back and look at the solutions together. All right, so we're back here, and it says use the above relationship to determine, in the first case, the angle subtended by an arc of 30 centimeters along a circle of radius 40 centimeters. So here we see that they give us A and they give us R. And so using this relationship, we'll be able to calculate the uh, arc length. The angle that's produced by this arc length. So again, imagine a circle. Okay, we have the radius of 40. Okay, and so here you're looking at an arc length of 30, and they want to know what's the angle that's produced by this here. Okay, now just by looking at that, I can see that this is going to be less than 1 radian, because this arc length is less than the radius, and I know an arc length of 40, the same as the radius, would give me 1 radian. So here, again, I could use either version of this relationship, but since I'm looking for the angle, I might as well use the first one. And so here we have that theta is equal to the arc length divided by the radius. And we see here that the radius doesn't even go in one full time around into that arc length. So here we have 30 over 40. And so here our uh, angle is 3/4 of a radian. Okay, remember radian's quite big. So remember it's about 57.5 degrees. So not surprising that, it's a fairly big angle. Okay, so here's one we would use it. And let's take a look at this one here. It says the distance traveled by the tip of a 12 centimeter second hand on a clock as it moves from 12 to 4. Okay, so let's, draw ourselves a little picture here. So let's draw, say, a clock. Now here we have the second hand, which moves from 12 to 4, which would be somewhere there. So there's 12, there's 4. And we realize that the second hand, of course the longer one, is going to represent the radius of this circle. Okay, so our radius is 12 centimeters, and what we're looking for is the distance traveled by the tip. So here's the tip as it moves along. So we realize that what we're looking for is an arc length. Okay, so I'm looking for an arc length. I have a radius, but if I want to try to use this relationship, okay, because they specifically tell me to use this relationship, what I'm going to need is an angle. Okay, so this is where, if I'm looking for this angle, theta, what I realize is it's the angle with the second hand going from 12 to 4. Okay, and that's when we realize from 4 to 8 and 8 back to 12 that this is 1/3 of a full turn. Okay, so theta is equal to 1/3 of a full turn, and of course a full turn is 2 pi radians. Okay, so in other words, my angle is 2 pi over 3 radians. Okay, now remember that this relationship was determined based on the fact that we were working with an angle in radians. So this does not work with an angle given in degrees. Okay, so now from here, I can now calculate that the arc length is given by the radius r times the angle theta, which is 2 pi over 3. And so here, do a little simplifying. So 4 times 2, so this is 8 pi centimeters. Or of course, I could find an approximation there. I guess that would be somewhere around 25 centimeters. Okay, now of course you could have found this arc length in a different way. You could have found the circumference because you know the radius of the circle and then divided that circumference by 3 because uh, you know uh, that this angle is 1/3 uh, of the angle going all the way around the circle. So certainly there were other ways to solve this, but we see that we can solve it quite easily using the arc length formula. So now before we move on, I want to take a look at number 4 here. It says use the relationship in 1. Okay. And actually, I guess really that should have been in 2. Now that I look at it, it should be relationship in 2. Okay, to justify that the angle defined in radians doesn't really have a unit. Now that's sort of interesting, as we say, well, it's radians. Here, this is 3/4 of radian. This is 2 pi over 3 radians. Okay, but let's take a look at what we're doing here. We said that another way of defining an angle in radians, okay, is to take an arc length and divide it by the radius of a circle. But when you see that the arc length is just a distance or length, okay, and the radius is again just another distance or a length, okay, and of course the assumption is that we're going to be measuring these in the same units. So like we had here, if we go back, this is 30 centimeters over 40 centimeters. You realize that this centimeter cancels out because it's like 30 times 1 centimeter over 40 times 1 centimeter. Okay, so the 1 centimeters in the numerator and denominator just reduce. Okay, so very often, the idea of radian says it's a measure without an actual unit. Okay, so that's why I could have written that answer as just 3 over 4. Okay, and as long as this is representing an angle, if you don't see a unit, the assumption is that it is representing radians. Okay, so here the assumption is that theta is in radians if no unit is written. Okay, and it's this idea that a radian is defined as dividing 2 measures of length. Hence, there's no unit associated to it. Okay, so essentially what we focused on now has been defining this new unit to represent angles. Okay, in some ways, it does seem as though it's a little more complex. 360 was a really nice number, lots of divisors, keeps things as whole numbers, whereas working in radians, seems to be bringing this complexity of having pi, show up a lot of the time. So we don't have these nice, round numbers that we're used to dealing with. So eventually we'll hopefully get to the place where we can understand why it's so important to work in this new unit. Okay. But certainly one nice thing about working in radians is that It's not like 360, which is just some arbitrary number. Okay, there's a physical significance to what a radian is. It can be defined using properties of circles for which angles are very important. All right. So we're now going to get into what I would say is more of the crux of this unit. Okay. And again, that's to work with angles. And the first thing that I want you to do is think about the trigonometric ratios. So mainly sine, cosine, and tangent, but also uh, cosecant, secant, and cotangent. Okay, and how in grade 10 your focus was purely on working with acute angles, angles that existed in a right angle triangle. Okay, and the way in which you define these trigonometric ratios, okay, was using this idea that when the angles in a triangle don't change, in other words, when you have similar triangles, the ratios of their side lengths stay the same. So the ratio of the opposite side to your angle and the adjacent side to your angle, this ratio didn't change whether I had this little small triangle or this larger triangle, which means that the ratio depends only on the angle. Okay, because once you know one of the angles is 90 degrees, the other two have to have, and you know this angle, well, the third angle, you know, just because they have to add up to 180. So this ratio between, say, the opposite and adjacent sides depends only on this acute angle. Okay. Uh, Similarly for any other two sides, opposite over hypotenuse, adjacent over hypotenuse, okay, hypotenuse over adjacent, if you want to look at secant, okay. So the reason why we focus on these ratios is because they depend only on this acute angle, okay. But that means you can only consider angles that are between 0 and 90 degrees. Or, of course, now we're not going to be talking in uh, degrees for much longer. We're going to be stating these angles in radians. Okay, but we want to move beyond just trig ratios for acute angles. Okay, so what I want you to think about is how we were able to define sine, cosine, and tangent for angles that could not be drawn inside a right angle triangle. Okay, so take a couple of minutes to try to remember and write down everything you know about how we used to define these angles. All right, so we're back. So here I gave you this little hint about considering the Cartesian plane. Okay, because when we're thinking about angles, again, this idea of thinking about angles as moving around in a circular motion. Okay, and as hopefully you remembered, is that if we want to define an angle in a Cartesian plane, it makes sense to have a starting point where all angles are going to start, so we can more easily compare them. It's hard to compare, an angle that starts at the positive x-axis to one that starts, 2/3 of the way between the positive x and the positive y. Okay, so we just choose the positive x-axis as the what we call the initial arm, okay, of the angle. And what we do is we move counterclockwise, okay, because we'd like to stay in the first quadrant for our, nice acute angles, okay. So here, if I draw this angle theta from my initial arm at the positive x-axis to what we call the terminal arm, all right, it creates an angle. Now, when we're working with these acute angles, well, hey, remember what we said, it doesn't matter what the size of the triangle is. We can just draw any triangle from that terminal on down, and lo and behold, we've got our right angle triangle, and we can talk about the opposite, the adjacent, and the hypotenuse sides of this triangle and define our ratios. Okay, but what happens if we're now, say, in the second quadrant, and this is the angle that I'm interested in? Okay, all of a sudden this angle cannot live inside a right angle triangle. So what we're going to do is we're going to reimagine how we can define the trig ratios on for an acute angle. So instead of thinking of the opposite side and the adjacent side and the hypotenuse side of this triangle, we realize that the adjacent length here just represents the x value of this point on the terminal arm. And the opposite side just represents the y value of this point on the terminal arm. So if I label this as my x value and label that as my y value, this point is just xy. Okay. And so if I were to take another point, say x1, y1, well, guess what? I just end up with another triangle that is similar to the original one. Okay, and of course we know, as we talked about earlier, the whole reason why these ratio of sides is workable is that it doesn't matter whether I take this smaller triangle or this larger triangle, the ratio of the side lengths are the same. So whether I'm working with xy or x1, y1, I get the same ratios. Okay, and so now this hypotenuse side, well, hey, wait a minute, if this represents x and that represents y, we realize that this hypotenuse, which we're going to call r, is just given using good old Pythagoras, or you can also think of it as being the distance formula between 0, 0 and this point xy. And what is the distance formula? Well, it's x minus 0 squared, which is x squared, okay, plus y minus 0 squared. So if you're not sure about this, go back and check the distance between 2 points on the Cartesian plane, and we realize that this distance formula is equivalent to Pythagoras in the acute triangle. Okay, so why is it useful to uh, reinterpret how we define our side lengths? Instead of thinking of them as side lengths, we think of them as coordinates of a point on the terminal arm and the distance of this point to 0, 0. Okay, because that means if I'm on some terminal arm where this angle, say phi, can't live inside a right angle triangle, it means I now have a way of defining my trig ratios. Okay, because again, this is just a point xy. So instead of defining my sine as opposite over hypotenuse, I define it as the y value divided by the r value. And I can do the same thing here, because once I have the point xy, even though it happens to be in the second quadrant, I can still determine the distance between these 2 points, r, and I can now define sine theta as being y over r. The y value of a point on my terminal arm, okay, divided by the r value, which is the distance of that point to 0, 0. And of course, you'll in a little bit see that you can define all your trigonometric ratios in this way. Okay, so if we go on to the next page, we'll see it's got a lot of the things that we talked about. So here now is my angle starting at the positive x-axis ending at a terminal arm. And so here, this is the terminal arm. So that's where the angle ends. Okay, XY represents any point on this terminal arm. Okay, so similar to the similar triangles that you would have worked with in grade 10. Okay, whether I pick this point, that point, doesn't matter. It produces the same ratios. Okay, now I'll save this one for a second. Okay, we have our quadrants, and we're going to talk, you'll hopefully remember a little bit why these quadrants are important. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, and what will also be useful to us, hopefully you remember that, is this related acute angle, which I'll label as RAA. Okay, which is the acute angle which is produced by the terminal arm to the x-axis, whichever part of the x-axis is closest. Okay, so say I'm in the third quadrant, or say fourth quadrant, so I don't mess it up there. Let's say I have an angle in the fourth quadrant. The related acute angle would be this angle here to the, in this case, positive x-axis. In this case here, the closest part was the negative x-axis. Okay, and these are going to be all important uh, uh, sort of characters in our story in working with angles on the Cartesian plane and their trigonometric ratios. Okay, so what I would like you to do now is to write out the 6 trigonometric ratios. Okay, but I don't want you to be using opposite, adjacent, hypotenuse. I want you to be using now our coordinates of the point on the terminal arm and the R value, which is the distance between 0, 0 and that point on the terminal arm. So now instead of talking about adjacent, you're talking about the x value. Instead of talking about opposite, you're talking about the y value. Instead of talking about a hypotenuse, you're talking about the r value. All right, so take a couple of minutes to write that up. All right, so we're back. So let's look at our 6 trigonometric ratios. So we already talked about the sine ratio. Okay, and the sine ratio now is given by the y value over the r value. Okay, here we have the cosine of the angle is now going to be the x value over the r value. And then we've got the tangent, which is going to be the y value over the x value. Because remember, the y value was equivalent to our opposite, and the x value was equivalent to our adjacent. Okay, and so now if I just want to define the the reciprocal trig ratios, so cosecant of theta, secant of theta, and cotangent of theta. So this is the reciprocal of the sine ratio, so that's just going to be r over y. Secant is just the reciprocal of the cosine ratio, so r over x, and cotangent is just the reciprocal of the tangent ratio, so x over y. All right. Now, a couple of other things that I do want to say here that will come up, but we might as well repeat them now, is how these quadrants really come into play. Okay, so we'll just talk really quickly about it, and hopefully, this sort of all came back to you. Is if I am defining the sine ratio as y over r, okay, cosine is x over r. Well, remember how we define this r value. It's the distance between 0, 0 and the point on the terminal arm. So that means r is always a positive number, okay? So that means when it comes to the sign, not S-I-N-E, but S-I-G-N, of these trigonometric ratios, you only have to be looking at the individual signs of the uh, x and y values. Okay, so here, if I look at sine, cosine, tangent, well, x and y are both positive in the first quadrant. That means that all of these ratios are going to be positive. So here we have sine, cosine, and tangent. Okay, similarly for the reciprocal ones, but I'll leave those for now, are all going to be positive. Whereas in the second quadrant, we notice that the y component is still positive, but the x component is negative. But look at the sine ratio. X doesn't come into play. So sine is still going to be positive. But if I look at cosine, I've got a negative value over a positive value. For tangent, I've got a positive value over a negative value. So we have that cosine and tangent are less than 0. Okay, and now we can make a similar argument here. Here, x and y are both negative. Okay, so the sine value and the cosine value will both be negative. But the tangent value, I'm dividing two negative numbers. Tangent is greater than 0 in this quadrant. Okay, and similarly, we have in the fourth quadrant, here the x component is positive, but it's only the y component that's negative. So here we see that sine is going to be negative. Okay, tangent is also going to be negative because I've got a negative value over a positive value. But the cosine, x is positive here, over, of course, r, which is always positive. And so here we have that the cosine is positive. Okay, and we're going to see in the next, the last example today, how this can be helpful in saving us a bit of time. All right. Now, what I want you to remember at this point is that there were 3 angles that were special. And the reason why these 3 angles were special is because we could determine the exact trig ratios for these particular angles. Okay. And now notice I'm talking about 3 special acute angles. There's other special angles, but I want you to focus on those 3 acute ones. So I'd like you to do is draw diagrams for those, but of course I don't want you to give me the diagram and the relationship in terms of degrees. I want you to think about what that would be in radians. Okay, so take a couple of minutes and recall those 3 special triangles. All right, so let's take a look here. And of course, I'm gonna, as you know, soon I'm gonna stop referring to the um, to the um, degree version of these angles. But of course, there's the 30-degree triangle. Okay, but remember what the relation was. Pi radians was 180 degrees. So if I think of 30 degrees, that's 180 degrees divided by 6. 180 divided by 6 is 30. So that means that's pi over 6 radians. Okay, so when I draw my first special triangle, okay, right angle here, I'm not going to label this the 30-degree angle. It's going to be the pi over 6. And of course, when there's no units, we assume it's radians. Okay, and you hopefully remember this set of numbers here. So the opposite side, the shortest side, is 1. Okay, the hypotenuse The longest side is 2. And then this third side, if you were to use Pythagoras, you see is root 3. All right. Now, of course, there was the 45-degree triangle. But here, 45 is just 180 divided by 4. Is 180 divided by 2 is 90, divided by another 2, 45. But of course, as we said before, 180 is the same as pi radians. So this is just pi over 4. So the 45-degree triangle is now the pi over 4 triangle. Okay. Try to draw it because, of course, you remember that the 45-degree triangle is isosceles. So here, the angle is pi over 4. And here, opposite side 1. This, of course, is also 1 since it's isosceles. Perform Pythagoras on this here. And this is, of course, root 2. And the last one, and sometimes people like to remember just 2 triangles because you realize that if this is 30 degrees, this side here is 60 degrees. Or, of course, we're going to write it in radians. I'm going to choose to write it as 2 separate triangles, okay? Because it just kind of helps to ensure that there isn't any confusion. Okay, so 60 degrees, well, that's just 180 divided by 3. So that's pi over 3 radians. Okay, and so that's the biggest of the angles. Okay, but essentially, it's just this triangle flipped around. So here my angle is pi over 3, but now the adjacent down here is the shorter side. Hypotenuse is still 2, and it's the height, the opposite side, that is longer than the adjacent side. Okay, so here are my special triangles, but as you would have seen last year, you can use these special triangles not just in the first quadrant. So definitely we have, pi over 6, pi over 4, pi over 3. You can recreate special angles in the other quadrants related to these special angles, okay? And furthermore, there's 4 other special angles. And remember, the reason why we call them special angles is because you can determine the exact trigonometric ratios. So try to think what other options you have for exact trigonometric ratios. All right, so take a couple of minutes or maybe more than a couple of minutes to try to remember what the special angles are, okay, that exist in one full turn of a circle. Okay, go ahead. Okay, so we're back. So before we move on to determining the other special angles that are related to these 3 here, let's talk about those other ones that I mentioned. So remember how we're defining sine, cosine, and tangent. We're just using points on the terminal arm. And hopefully you remembered that I can take a point on, well, a very special terminal arm. What about at 0, an angle of 0? Okay, that's an angle, as 0 is a number. And you realize that at 0, you can take the point 1, 0. And you know the distance from 0, 0 to 1, 0 is 1. So you realize that you can easily determine the exact trig ratios for an angle of 0. But very similar to taking a point on the positive y-axis. So let's see what angle this would be. Well, remember, 180 degrees is pi, so 90 degrees is half of 180. So this would just be pi over 2. Okay, and again, this is the point 0, 1. So you know the y value, you know the x value, and the distance, again, from this point to the origin is just 1. So you can calculate the exact trig ratios. And you could do the same thing at pi on the negative x-axis, because you can just take the point, -1, 0, and determine all of them. And you can do the same thing here. All right, at the negative y-axis, take 0, -1. So this is also special angle. So let's try to figure out what this would be here. Okay, and this is where you're going to see me use a little trick that I'm going to use later on. Is think of this as pi over 2. This is 2 pi over 2, okay, which is the same as pi. And here I'm adding another pi over 2. So this angle here is 3 pi over 2. And of course, if I add another pi over 2, I get 4 pi over 2, which is 2 pi. But that essentially takes me back to 0. And of course, that's going to be an important part of the use of these trigonometric ratios. Okay, is this idea that once I do a full turn around the circle, everything starts to repeat itself. Okay, so we'll keep that in the back of our brains. All right, so now let's try to find other special angles. Okay, so the next special angle, if I were thinking of it in terms of degrees, so this would be 90, the next one would be 120. Okay, but instead of thinking of this as 120, all right, I'm going to do a little trick here. So if this is pi over 3, then 120, what would be left here? Be 60 degrees, okay, or pi over 3. So here I have a pi over 3. Here I have another pi over 3. If I do the full half turn, it would be 3 pi over 3. So this one is 2 pi over 3. Now I could do the conversion from 120 to radians, but what I want you to think about is learning how to work with these angles in radians. This is pi over 3, another pi over 3 brings me to 3 pi over 3. Okay, let's now go for the next one. Okay, here we've got pi over 4, 45 degrees, plus another pi over 4 gives me pi over 2, like 90 degrees. If I add another pi over 4, this is going to be 3 pi over 4. Okay, like adding 90 to 45, this would be the 135 degree angle. But I'm thinking of it in terms of radians. So pi over 4, 2 pi over 4, 3 pi over 4. And now we've got this one here, not surprisingly, is going to be related to the pi over 6. Okay, but if this is pi over 6, the related acute angle on this angle is also going to be pi over 6. Okay, so remember, going half a turn is pi, but pi is the same as 6 pi over 6. 6 over 6 is 1. So what I'm going to think of this as is 6 pi over 6 minus pi over 6. This is going to be 5 pi over 6. Okay, and I could keep going. Okay, so let's start listing some of these. So we have 0, we have pi over 6, we have pi over 4, we have pi over 3, and we have pi over 2. And there's my first quadrant. Then we're going 2 pi over 3, 3 pi over 4, 5 pi over 6. Okay, and then of course we get to pi 180 degrees. So now I'm going to do similar to what I did before. If this is pi over 6, sorry, this is 6 pi over 6, and now I add another pi over 6, this brings me to 7 pi over 6. That's going to be the next one. Okay, now I want to use the pi over 4. So instead of thinking of 180 or pi as pi, I'm going to think of it as 4 pi over 4 plus another pi over 4, like another 45 degrees, and that brings me to 5 pi over 4. And there's my next one. And this is how I'm going to just keep going. Okay, so here, instead of being pi, I'm going to think of this as 3 pi over 3 plus another pi over 3. That's like another 60 degrees. And that brings me to 4 pi over 3. Okay, and what I want you to see, what I'm doing, is I'm just working with different denominators. Okay, if I want to work with denominator 6, I think of pi as 6 pi over 6. If I want to work in fours, I think of this as 4 pi over 4. If I want to work in over 3, this is 3 pi over 3. Okay, and you see now that I'm, and then of course my next one here is 3 pi over 2, which is like my 270. Okay, and now I'm going to use another little trick. Instead of thinking of pi as, say, 3 pi over 3, I'm now going to think of 2 pi as 6 pi over 3. So if I do 6 pi over 3, which is a turn all the way around, and I subtract pi over 3, this brings me to 5 pi over 3. Instead of thinking of 2 pi as 2 pi, I think of it as 8 pi over 4. And I'm going to subtract pi over 4 to give me 7 pi over 4. Okay, so again, all I'm using is equivalent fractions. Okay, guess what? Instead of thinking of this as 2 pi, I'm going to think of one turnaround as 12 pi over 6 minus 1 pi over 6. It's going to give me 11 pi over 6. And there is my last special angle. I guess I could end it off as getting all the way around and then 2 pi. And you see how now if I want to keep going, I would just take 2 pi and add pi over 6, or add pi over 4, or add pi over 3, and I can keep going round and round and round and round. Okay, so should you be memorizing this diagram? Should you be memorizing all these angles? I would say certainly not. What you want to get used to is being able to generate these angles by using your knowledge of fractions. Okay, so here when you want to try to remember what angle this is, you do 6 pi over 6 minus pi over 6, 5 pi over 6. If I want to remember this angle here, I go 3 pi over 3 plus 1 pi over 3, 4 pi over 3. And it's just about using your facility with special angles to determine your facility with fractions to help you determine whatever special angle you're interested in. Okay, so what I want you to try to do is see if you can remember how to determine the trig ratios of these special angles. Now, of course, you wouldn't have been dealing with 2 pi over 3 last year. You would have been dealing with 120 degrees. Okay, you wouldn't have been dealing with 3 pi over 2. You would have referred to this as 270 degrees. But what I want you to force yourself to do is start to become comfortable, slowly, working with angles and radians. Okay, so you should take, maybe 5-10 minutes to work on as many of these as you can and see how far you get. And then you can come back and check the solutions. Okay, go ahead. All right, so we're back here. And I'm actually going to try not to refer to this diagram, okay? Because I want to try to work with these angles. I want to learn how to work with them on a case-by-case basis. All right. So I'm going to draw this in order to get the angle here. Is I'm going to try to draw 2 pi over 3. Okay. So the first thing I notice is that this is less than pi. It's 2/3 pi. So the way I might think about it is this is pi over 3. this is going to be 2 pi over 3. That's going to be 3 pi over 3. So my angle is going to be in the second quadrant. Okay, and there's the angle, 2 pi over 3. Now remember, we talked about quadrants. I know that the sine value in the second quadrant should be positive. Okay, now this is where we're going to bring in that related acute angle that we talked about. Now, here we're talking about an acute angle. If it's an acute angle, it means it can be drawn inside a triangle. And this is where we use the trick of drawing one of our special triangles. Because if this angle here is 2 pi over 3, then the related acute angle to the negative x-axis is pi over 3. Okay? And this is where I'm going to make use of my special triangle. I know that special triangle is 1, 2, root 3. But remember, pi over 3 is not our angle. Our angle is 2 pi over 3. So here, in order to find the sine value, I'm actually working with a point on this terminal arm. But what would this point be? Well, remember, this represents the x value, and this is where we remember that the x value is negative and the y value is positive. Okay, but it's a little annoying to have to write this point every time. So as a quick reminder, what I would do is, even though the side length is positive 1, I just put a negative 1 as a reminder that what I'm really working with is not the side length, but the x value of that point. And this allows me to correctly interpret the sine of the x component. Now in this case here, I'm not working with the x component because it's the sine value, SINE, that I'm looking for. And so here off my graph, I can just read, sine is y over r, so root 3 over 2, and positive as we expected. Okay, now that is one way to do it. That's the more direct way of thinking about it, because you're actually thinking about it in terms of this point on the terminal arm. Some people use a trick and say, well, look, I'm just going to work with my pi over 3 special angle, okay? And remember that because I'm in the second quadrant, the sine value is positive. And that's perfectly valid to use what's called that cast rule. So if we go back to this here, okay, the cast rule would be, here cosine is positive, all of them are positive, the sine is positive, tangent is positive, hence the old cast rule. So if you're comfortable working with that, you're going to see me drawing the diagram all the time, because I really want to reinforce the idea that we're working with points on the terminal arm. So I'm going to do the same thing here. I'm going to draw myself a little diagram. So here, 5 pi over 4. So I know I'm working with fractions of 4. So pi would be 4 pi over 4. So I need to go one more pi over 4 to get to 5 pi over 4. That means my related acute angle is pi over 4. And from here, -1, -1, root 2. Okay, so I'm using the side lengths to help me get my x value and my y value. But of course, I have to remember that the x value is negative and the y value is negative. So from here, cosine x over r, -1 over root 2. And of course, cosine should be negative in the third quadrant. Okay, here, 11 pi over 6. Well, this looks a lot like 12 pi over 6, which is a full turnaround. 12 pi over 6 minus 1 pi over 6. There's the angle I'm interested in is 11 pi over 6, and my related acute angle is pi over 6. Okay, and of course my side lengths are Well, this is -1 because the y is negative, okay, to positive root 3 because the x value is positive. So tangent, of course, is y over x. So -1 over root 3. Okay. Now let's go to sine of 3 pi over 2. And this, of course, is not going to be a special triangle because 3 pi over 2 is on my axis. So here I cannot relate it to a special triangle, but what I can use is the easiest point on the negative y-axis, 0, -1, and of course the distance between this point and the origin is just 1, and so now I can calculate the sine value, which is y over r. -1 over 1 is -1. Okay, and these types of examples are going to be useful because as I try to develop information about these trig ratios, okay, it's going to be nice to have some trig ratios for which I've got exact values to work with. Okay, so just to do a quick recap, it's very important that you remember how we define these trig ratios. We don't define them based on opposite, adjacent, hypotenuse, because now we're dealing with angles that cannot fit inside an acute triangle. We are using a point on the terminal arm and the distance between that point and 0, 0. Okay. When we're defining angles, we define them from the positive x-axis going counterclockwise. If we were to go clockwise, well, we're just going in the opposite direction. So as we'll recall later on, those are just going to represent our negative angles. We allow for negative angles. Okay. You should know where the trig ratios are positive and negative. You should know the reciprocal trig ratios, and you should become familiar with the special angles now given in radians. Okay, that's it for this one.